Welcome to chemistry, the hydrolysis of salts. When a salt dissolves in water, its ions may interact with water molecules and affect the pH of the solution. This process, known as salt hydrolysis, is fundamental to understanding acid-base equilibrium in aqueous solutions. Some salts produce acidic solutions, others produce basic solutions, and some have no effect at all. In this presentation, we will explore the four categories of salts: the hydrolysis constant pH, the degree of hydrolysis, and pH calculations for each type. Through 5 quiz questions and 5 fully worked problems, you will master this essential topic of ionic equilibrium. Pure water is neutral with pH 7.00 because the concentrations of hydronium and hydroxide ions are equal at 1.0 times 10 to the negative 7 molar. When a salt dissolves, its ions may react with water, shifting this equilibrium. A cation from a weak base can donate a proton to water, producing hydronium ions and making the solution acidic. An anion from a weak acid can accept a proton from water, producing hydroxide ions and making the solution basic. Ions from strong acids or strong bases are spectators. They do not undergo hydrolysis because their conjugate acid or base is too weak to react with water. The net effect on pH depends on which ions undergo hydrolysis and to what extent. This is summarized by the rule of thumb. The stronger the parent acid or base, the weaker the hydrolysis tendency of its conjugate ion. Every salt can be classified into one of 4 categories based on the strength of its parent acid and base. First, salts from a strong acid and a strong base, such as NaCl from HCl and NaOH. These produce neutral solutions because neither ion hydrolyzes. Second, salts from a strong acid and a weak base, such as NH4Cl from HCl and NH3. The cation from the weak base undergoes hydrolysis, producing an acidic solution. Third, salts from a weak acid and a strong base, such as NaCH3COO from CH3COOH and NaOH. The anion from the weak acid undergoes hydrolysis, producing a basic solution. Fourth, salts from a weak acid and a weak base, such as NH4CH3COO from CH3COOH and NH3. Both ions hydrolyze, and the pH depends on the relative strengths of Ka and Kb. If Ka exceeds Kb, the solution is acidic. If Kb exceeds Ka, it is basic. If they are equal, the solution is neutral. When a salt like ammonium chloride dissolves in water, it dissociates completely into ammonium ions and chloride ions. The chloride ion from the strong acid HCl is a spectator. It does not react with water. The ammonium ion, however, is the conjugate acid of the weak base ammonia. It donates a proton to water, producing hydronium ions and ammonia. This reaction is the hydrolysis step, and it establishes an equilibrium. The equilibrium constant for this reaction is called the hydrolysis constant, KH, and it equals Kw divided by Kp. For ammonium ion, KH equals 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which equals 5.6 times 10 to the negative 10. The production of hydronium ions makes the solution acidic, typically with a pH between 4 and 6 for moderately concentrated solutions. The extent of hydrolysis is quantified by the degree of hydrolysis H, which equals the square root of KH divided by the concentration. To calculate the pH of a salt from a strong acid and weak base, we set up an equilibrium expression. Consider concentration C of the salt. After dissociation, the cation concentration is C. The cation undergoes hydrolysis. M+ reacts with water to produce H+ and MOH. Let X be the concentration of H+ at equilibrium. The equilibrium constant KH equals X squared over C minus X. For typical concentrations and KH values, the approximation C minus X approximately equals C holds when X is much smaller than C. This gives us X equals the square root of KH times C. Since X equals H plus concentration, the pH equals negative log of H plus. Substituting KH equals Kw over Kb, and simplifying, we get the formula pH equals 1/2 times pKw minus pKb minus log C. At 25 degrees Celsius, pKw is 14.00. So for a 0.10 molar ammonium chloride solution with pKb of ammonia equal to 4.74, the pH equals 1/2 times 14.00 minus 4.74 minus -1, which equals 5.13. When sodium acetate dissolves in water, it dissociates completely into sodium ions and acetate ions. The sodium ion from the strong base NaOH is a spectator. The acetate ion, the conjugate base of the weak acid, acetic acid, accepts a proton from water, producing hydroxide ions and acetic acid. This hydrolysis reaction produces hydroxide ions, making the solution basic. The hydrolysis constant Kh for the acetate ion equals Kw divided by Ka. Since Ka of acetic acid is 1.8 times 10 to the negative 5, KOH equals 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, which equals 5.6 times 10 to the negative 10. The pH of such solutions typically ranges between 8 and 10. The hydroxide concentration is the square root of Kh times C, and the pOH equals 1/2 times pKw minus pKa minus log C. The pH is then 14 minus pOH. The pH calculation for salts from weak acid and strong base follows the same logic as the acidic case, but with hydroxide instead of hydronium. For the salt Na with concentration C, the anion A- undergoes hydrolysis. Let Y be the concentration of OH- at equilibrium. The hydrolysis constant Kh equals Y squared over C minus Y. Approximating C minus Y as C gives Y equals the square root of Kh times C. Since Y is the hydroxide concentration, the pOH equals negative log of Y. The pH equals 14 minus pOH. Substituting Kh equals Kw over Ka gives us the formula pOH equals 1/2 times pKw minus pKa minus log C. For a 0.10 molar solution of sodium acetate, Ka of acetic acid is 1.8 times 10 to the negative 5, so pKa is 4.74. The pOH equals 1/2 times 14 minus 4.74 minus -1, which equals 5.13. The pH, therefore, equals 14 minus 5.13, which is 8.87. The solution is clearly basic. When both the cation and ion undergo hydrolysis, as in ammonium acetate, the situation is more complex. The cation M+ produces H+ via hydrolysis, while the anion A- produces OH-. The net pH depends on which hydrolysis reaction is stronger. For any WiWb salt of concentration C, we use the formula that the hydronium concentration equals the square root of Kw times Ka divided by Kb. Taking negative logarithm gives pH equals 1/2 times pKw plus pKa minus pKp. If Ka of the weak acid equals Kb of the weak base, the solution is neutral. If Ka is greater than Kb, the solution is acidic. If Kb is greater than Ka, the solution is basic. For ammonium acetate, Ka of acetic acid is 1.8 times 10 to the negative 5, and Kb of ammonia is 1.8 times 10 to the negative 5. Since they are equal, a solution of ammonium acetate is neutral. For ammonium cyanide, Ka of HCN is 4.9 times 10 to the negative 10, and Kb of ammonia is 1.8 times 10 to the negative 5. Since Kb is greater than Ka, ammonium cyanide solutions are basic. The hydrolysis constant Kh quantifies the extent of hydrolysis for a particular ion. For a cation M+, Kh equals Kw divided by Kb of its conjugate base. For an anion A-, Kh equals Kw divided by Ka of its conjugate acid. The degree of hydrolysis, H, is the fraction of the total salt that has undergone hydrolysis. For acidic salts, H equals H plus concentration divided by the initial salt concentration C. For basic salts, H equals OH minus concentration divided by C. The degree of hydrolysis increases as the salt concentration decreases and as the parent acid or base becomes weaker. For dilute solutions, H equals the square root of KH divided by C. This means that more dilute solutions have a higher degree of hydrolysis. Temperature also affects hydrolysis. Higher temperatures increase Kw and therefore increase KH and the degree of hydrolysis. Understanding KH and H allows us to predict the pH and behavior of salt solutions under various conditions. Salts of polyprotic acids add another layer of complexity. Consider sodium bicarbonate. The bicarbonate ion HCO3- is amphoteric. It can act as either an acid or a base. It can donate a proton to form CO3-2- or accept a proton to form H2CO3. For such amphoteric species, the pH of the solution is given by 1/2 times pKa1 plus pKa2. For carbonic acid, pKa1 is 6.35 and pKa2 is 10.33. So the pH of a sodium bicarbonate solution is 1/2 of 6.35 plus 10.33, which is 8.34, which is basic. For sodium carbonate, the carbonate ion CO3-2- is the conjugate base of bicarbonate and undergoes basic hydrolysis with KH equals Kw divided by Ka2. This gives an even more basic solution. For sodium dihydrogen phosphate, the H2PO4- ion is also amphoteric with pH equals 1/2 of pKa1 plus pKa2, which for phosphoric acid is 4.68, giving an acidic solution. Each polyprotic salt requires careful consideration of which hydrolysis equilibrium dominates. Quiz question 1. Which salt produces an acidic solution when dissolved in water? Option A, NaCl. Option B, KNO3. Option C, NH4Cl. Option D, ANH3COO. Take a moment to think about your answer. Quiz question 2. What is the hydrolysis constant KH for the acetate ion CH3COO-? Ka of CH3COOH is 1.8 times 10 to the negative 5. Option A, 1.8 times 10 to the negative 5. Option B, 1.0 times 10 to the negative 14. Option C, 5.6 times 10 to the negative 10. Option D, 5.6 times 10 to the negative 5. Think carefully about the relationship between Ka and Kh. Quiz question 3. The pH of a 0.10 molar NH4Cl solution is approximately 5.13. What is the Kb of NH3? pKw is 14.00. Option A, 1.8 times 10 to the negative 5. Option B, 5.6 times 10 to the negative 10. Option C, 1.0 times 10 to the negative 14. Option D, 1.8 times 10 to the negative 4. You will need to use the pH formula for acidic salts. Quiz question 4. Which statement about NH4CH3COO ammonium acetate is true? Option A, the solution is always strongly acidic. Option B, the solution is neutral because Ka equals Kb. Option C, the solution is always strongly basic. Option D, only the cation undergoes hydrolysis. Quiz question 5. What is the degree of hydrolysis H of a 0.010 molar solution of NaCH3COO? KH is 5.6 times 10 to the negative 10. Option A, 5.6 times 10 to the negative 8. Option B, 2.4 times 10 to the negative 4. Option C, 5.6 times 10 to the negative 5. Option D, 1.0 times 10 to the negative 2. Problem 1. Calculate the pH of a 0.150 molar solution of ammonium chloride. Kb of NH3 is 1.8 times 10 to the negative 5. We will solve this step by step. Step 1. NH4Cl dissociates completely, so the initial NH4 plus concentration is 0.150 molar. Step 2. Calculate the hydrolysis constant KH equals Kw divided by Kb. 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 equals 5.56 times 10 to the negative 10. Step 3. Set up ice table. NH4 plus is 0.150 minus x, H plus is x, NH3 is x. Step 4. KH equals x squared over 0.150 minus x. Since KH is very small, we approximate 0.150 minus x as approximately 0.150. Step 5. X equals square root of 5.56 times 10 to the negative 10 times 0.150, which equals 9.13 times 10 to the negative 6 molar, which is the H plus concentration. Step 6. Check the approximation. 9.13 times 10 to the negative 6 divided by 0.150 is 0.0061%, much less than 5%, so the approximation is valid. Step 7. pH equals negative log of 9.13 times 10 to the negative 6, which equals 5.04. The final answer is pH equals 5.04. Problem 2. Calculate the pH of a 0.200 molar solution of sodium acetate. Ca of acetic acid is 1.8 times 10 to the negative 5. Step 1. Sodium acetate dissociates completely, so the acetate concentration is 0.200 molar. Step 2. GAH equals Kw divided by Ka. 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 equals 5.56 times 10 to the negative 10. Step 3. Set up ice table. Acetate is 0.200 minus Y. O minus is Y. Acetic acid is Y. Step 4. KH equals Y squared over 0.200 minus Y. Since KH is very small, approximate. Y equals square root of 5.56 times 10 to the negative 10 times 0.200. Step 5. Y equals 1.054 times 10 to the negative 5 molar, which is the OH minus concentration. Step 6. POH equals negative log of 1.054 times 10 to the negative 5, which equals 4.98. Step 7. pH equals 14.00 minus 4.98, which equals 9.02. The solution is basic. Final answer, pH equals 9.02. Problem 3. A 0.0500 molar solution of a salt Na at 25 degrees Celsius has pH equals 8.50. Find Ca of the weak acid Hi and the degree of hydrolysis H. Step 1. POH equals 14.00 minus 8.50, which is 5.50. Step 2. O minus concentration equals 10 to the negative 5.50, which is 3.16 times 10 to the negative 6 molar. Step 3. For Wa and Sb salt, the OH minus concentration equals the Ha concentration at equilibrium, which is 3.16 times 10 to the negative 6 molar. Step 4. GaOH equals OH minus squared divided by C. 3.16 times 10 to the negative 6 squared is 1.0 times 10 to the negative 11, divided by 0.0500 gives 2.00 times 10 to the negative 10. Step 5. Ca equals Kw divided by Kh. W 1.0 times 10 to the negative 14 divided by 2.00 times 10 to the negative 10 equals 5.0 times 10 to the negative 5. Step 6. The degree of hydrolysis H equals OH minus divided by C, which is 3.16 times 10 to the negative 6 divided by 0.0500 equals 6.32 times 10 to the negative 5, which is only 0.00632%. Final answer. Ca equals 5.0 times 10 to the negative 5, and H equals 6.32 times 10 to the negative 5. Problem 4. Find the pH of a 0.100 molar solution of ammonium cyanide. Ca of HCN is 4.9 times 10 to the negative 10. Kb of NH3 is 1.8 times 10 to the negative 5. Step 1. Both NH4 plus and CN minus undergo hydrolysis because this is a WaW salt. Step 2. For a WaWb salt, H plus concentration equals the square root of Kw times Ka divided by Kb. Step 3. Ka of HCN is 4.9 times 10 to the negative 10, and Kb of NH3 is 1.8 times 10 to the negative 5. Step 4. H plus equals square root of 1.0 times 10 to the negative 14 times 4.9 times 10 to the negative 10 divided by 1.8 times 10 to the negative 5. Step 5. This equals the square root of 2.72 times 10 to the negative 19, which is 5.22 times 10 to the negative 10 molar. Step 6. pH equals negative log of 5.22 times 10 to the negative 10, which equals 9.28. Step 7. Since Kb is greater than Ka, the solution is basic, with pH above 7. Our result confirms this. Final answer. pH equals 9.28. Basic solution. Problem 5. Calculate the pH of a 0.100 molar solution of sodium bicarbonate. For carbonic acid, Ka1 is 4.3 times 10 to the negative 7 and Ka2 is 5.6 times 10 to the negative 11. Step 1. NaHCO3 dissociates completely into Na+ and HCO3-. Step 2. The bicarbonate ion is amphideric. It can donate a proton using Ka2 or accept a proton using Kb equals Kw divided by Ka1. Step 3. For amphideric species, the H+ concentration equals the square root of Ka1 times Ka2. Step 4. pKa1 equals negative log of 4.3 times 10 to the negative 7, which is 6.37. Step 5. pKa2 equals negative log of 5.6 times 10 to the negative 11, which is 10.25. Step 6. pH equals 1/2 of 6.37 plus 10.25, which is 16.62 divided by 2, equals 8.31. Step 7. The bicarbonate ion behaves as a weak base in solution, giving a pH greater than 7. Final answer, pH equals 8.31. Let us consolidate everything we have learned about the hydrolysis of salts. Salt hydrolysis is the reaction of salt ions with water affecting the pH of the solution. There are 4 types of salts based on parent acid-base strength. Salts from strong acids and strong bases give